Okay, so let's get started. So today we are going to do a memory management refresher. Again, that's a set of concepts you should have learned in an undergrad OS class, but I want to make sure everyone is on the same page. So we are going to go through that material quickly, and then next class I'm going to talk about memory management in Linux. Okay, and you'll see some of these concepts translate directly. But before I get started on the refresher, and we are going to cover all of those techniques: contiguous memory allocation, paging, segmentation, and demand page virtual memory. But before we start, let me say a little bit about the lab. So lab 1 is done, right? So you turned it in. There's still one small piece of lab 1 that everyone needs to be aware of, which is you have to sign up soon for a in-person 10-minute presentation with your group. Okay, that's part of the grading of the lab. The lab itself is done, and I wanted to be sure you come prepared for what is going to be done in that 10 minutes. So we decided to have it structured in terms of what is going to happen. So you have 6 minutes to present to us what you have done. Okay, so you can essentially, as part of that presentation, you have to bring your machine. You have to show us that your code runs. Right? Basically execute the virtual machine and show that it's actually your system call is actually working. Okay? It would be fairly straightforward. So it's like a tiny demo that you are going to give showing the code works, and then spend a few minutes talking about your design of the code. Right? So it's talk a little bit about what you did, how it works, and maybe you can show us your code on GitHub and things of that. Okay? And then we leave 4 minutes for Q&A, where we will ask you questions about your project and what issues you might have faced, or ask you to explain some aspect of your code and things of that. Okay? So I think there are two goals here. One is to actually have you get a little bit of experience presenting your work. Okay? We don't have any formal presentations in this class. This is pretty much the only time when you actually get to present to us, as opposed to us always presenting to you. So it's a somewhat lightweight. There's nothing very formal about it, but we decided that is the structure that you should all be aware of. Okay? We will have a sign up sheet soon. So you will sign for a block of time, maybe 30 minutes, although your chunk of that 30 minutes will be only a 10-minute slot. But we cannot be very precise because of maybe a couple minutes overflow. So plan to be present for your 30-minute block, and your slot will be either the first, second, or the third slot within that 30-minute chunk. Okay? So any questions about this? Yes, please.
Will every lab have these short presentations?
Yes, the question is, will every lab have these presentations? The plan is that we would like you to spend a little bit of time thinking how you present your stuff. Okay, so we will do this for every lab. Yes?
Like what days are you thinking that you can have times for presentations?
Okay, so questions, what days of the week? We haven't yet figured that out, but we know that you will have class conflicts and so on, so don't worry about that. We will ensure that they're spread out well enough that you should be able to find something that works for you. If not, we'll make more slots. So that should not be an issue. Okay, we will be flexible there. Okay? But it should hopefully happen sometime this week, is my thinking. Any other questions? Okay. So that's lab 1. Okay, now let me say a little bit about lab 2. I don't know how many of you have started lab 2. You should, because as you can imagine from what happened in lab 1, the complexity is a little bit higher in lab 2 than lab 1. Is going to get one more level of complexity in lab 3 and so on. So labs will get harder as you progress. So you should not try to start at the last minute and run out of time because you're seeing unexpected issues and so on. So if you haven't started already, please do. And if you have started, you probably would have seen lots of posts on Piazza asking all kinds of questions. I just wanted to explain at a very high level what we had intended and basically what clarifications are being posted on Piazza. Okay? So the first thing in the lab is that we gave you a sample scheduler, and the intent was for you to understand how to implement the CPU scheduling algorithm. And it was a FCFS scheduler. It was basically a very simple scheduler. It should be clear from the questions that were asked, and answers provided, that it was not intended to be a fully correct FCFS scheduler that captures every possible corner case. Because the intent was, here is how you implement a CPU scheduler, these are the places you need to touch in the kernel, and here's something that kind of works by and large. Right? So that was the intent. So there are many questions about what about this, what about that. Valid questions. When you implement your scheduler, if you want to take those issues into account, please do. Right? Our expectation is not that you will capture every single corner case that you can think of when you try to do CPU scheduling, but by and large you should have a functional scheduler. Okay, there are two that you will build, as you know. There's a random scheduler and a lottery scheduler. Both are randomized. So you want something that works. Okay? But if you feel like you have to address some issues that that you might actually think about, that's fine too. Okay? We are giving you that design freedom. Okay? So that's something I want you to keep in mind. Okay? So the FCFS scheduler is just an example. Okay? So that's not, you are not going to be graded for the part that involves FCFS scheduling. That's just to show you how things work. So go through that exercise, understand what is involved, and then do the actual lab. Okay? Is that clear? Any questions? Okay. So that was the first thing I wanted to mention. The second thing is there's quite a bit of confusion about what we had asked you to measure. Because we said, show us that your scheduler actually works, and the way we wanted you to do this is run some sample processes and do some measurements and plot a graph. Okay? That's another skill that you need to learn, which is to understand how you evaluate your code. In particular, in this case, you are evaluating the performance of your code. Okay? Now, as part of that, we have said go and measure waiting time, and there's lots of questions about what is waiting time and so on. Right? So if you go back to my CPU scheduling lecture, okay, where I presented various policies, you will see that waiting time is very clearly defined in there. Okay? You take the turnaround time of the process. The turnaround time is you take the start time when the process started, you take the end time when the process ended. The difference between the two is the time for which the process was active. That's the turnaround time. Okay? So you take the turnaround time of that process. Okay? And then the waiting time is from that turnaround time, how much time were you actually waiting, meaning not executing. Right? So if you say this process was active for 10 seconds, of that 10 seconds it actually executed on a processor for 3 seconds, it follows that it was waiting for something or the other for the remaining 7 seconds. Right? So you take the turnaround time, if you can figure out how to calculate the execution time, the difference between the two will give you waiting time. Okay? That is how those toy examples that we gave you in the CPU scheduling lecture actually computed the waiting time. Okay? You can do the same thing. Okay? And there are some posts that clarify how do you do this. So clearly the turnaround time you can figure out by measuring the wall clock time when you start the process, measuring the wall clock time when the process ends. Okay? And the difference between the two is the turnaround time. Okay? Now the question is, how do you figure out the time for which your process executed? You can use a simple utility like time, which is going to tell you for how long that process actually executed. That's good enough. Okay? Is that clear? Any questions on this? There are lots of questions about how do you compute this and so on, or what it even meant to calculate waiting time. Okay? Now the TA has actually simplified your work for you and said, we will even accept measurements of just turnaround time if you don't want to measure waiting times. Okay? The original assignment said go measure waiting times because you can understand the effectiveness of the CPU scheduler by actually calculating waiting times and seeing how they vary. Okay? But if that seems to be complicated, it really shouldn't. But if it is, then you can still report turnaround time and we'll still accept that. Okay? But if you can go and try to measure waiting time, it will be an interesting exercise. Any questions on this? Okay, so that's that. And then the several other questions about what your CPU scheduling policy is expected to do. Okay? So the first thing is you are not expected to change anything that is associated with the system process. System processes are assigned to predefined queues in the system. Okay, the kernel runs on Q0 or Q1, whatever it's called, the lowest queue, which is the highest priority, and so on. So don't touch the system processes, let them be. Okay? all we are doing here is putting all user processes in a single queue. Normally they would be in multiple priority levels. You put them in a single queue and you either do FCFS scheduling, you do random scheduling, or you do lottery scheduling. That's all we are expecting you to do. Okay? So you are not expected to actually change the priorities of system processes or anything like that. Okay? So they get scheduled still, and when it's time to schedule a user process, in this case they are all sitting in one queue, so your policy will either do FCFS in the sample case or random or lottery. Is that clear? Okay. So that's the other clarification we wanted to provide. Okay, and then of course you can say, how do you figure out if your system process is or not? There are some clarifications we provided, saying there's a call that says is system proc. If it's true, you know that's a system process, otherwise it's a user process. So you can figure out whether a process is a system process or not using the very simple kernel call. Okay. Okay. So the last thing I want to mention is there are some subtleties that you have to keep in mind, some which we still don't understand. One of them is there are multiple random functions that Minix implements. One of them doesn't work. We still don't know why. So we just figured that you should use the one that works and not worry about why the other one doesn't work. Okay? So it's causing some sort of a deadlock. I can't understand the code why it's causing deadlock. So essentially don't use srand or srandom, use rand or random, and then you should be fine. And then there are some other subtleties saying when a process unblocks it's going to get rescheduled to a highest priority level, then how do you change its priority level? We gave some clarifications on that. If you want to address these subtleties, go look at the Piazza post and try to figure that out. But as I said, if you do the basic things, that's good enough for this assignment. Okay. The assignment is due next week. Okay. So it will come up soon, so don't wait until the last minute. Okay. And then I think I made a post on Piazza. The exam is the week after next. Okay. It's on March 10th. Okay. That's a Tuesday, but it won't be an in-class exam. Okay. So that day there will be no lecture. Okay. And instead we'll have an evening exam, just so that there is no time pressure. Okay, so we can have more time. If it's an in-class exam, we have to end when the class ends, and then that's it. Okay, here if you start at 7, it's tentatively scheduled from 7 to 8:30, which should be plenty of time, but there shouldn't be any time pressure where you have another class or anything like that. Okay, so and the other thing is the room number. It's not going to be here in this room. Don't come here. Go to the computer science building 142. Okay, I put a note on Piazza, I put a note on the class web page. I'm also going to send an email, so you should not have any confusion when the exam is, where to go and so on. Okay, it will be posted in multiple places. Okay, that exam will be closed book, closed notes, 90 minutes. Okay, and it's the only exam, there's no final exam or anything like that. All right, any questions about any of these logistics, lab, exam, anything else? Yes, please. Okay, so let me think. Question is sample exam. There has never been an exam for this class because there's never been a class. So I can't give you last year's exam, but I might make some sample questions so you get a feel for what to expect. Okay. Any other questions? Okay. So if there's anything else, come to office hours, post a question on Piazza. We are still available anytime to help. Okay. All right, so let's move on and go back to our memory management refresher. As I said, this is again material from an undergrad class. It's kind of took 4 classes worth of material, and I'm going to just cover it quickly. It's more important for you to ask questions so I can spend time on the right things to clarify what you may not have absorbed from that class or forgotten and things of that sort. Okay. And then I'll post, it's already, everything is already posted, but I have more slides here than I'm going to cover simply because I just wanted to give that as a reference. Okay, because the next lab is going to be on memory management, so I wanted you to have all the background needed to do the lab. Okay. All right, so this is the picture you should keep in mind. This is the same picture I showed in lecture 2, which is basically a picture of a machine architecture. So that there are 4 key pieces. There is the CPU, there's the memory controller, there's the CPU, there's memory controller, there's the I/O devices, I/O controllers, and the system bus that interconnects them. So in this case, we are actually going to focus on the memory. Okay, the assumption is that your program sits on disk. When you start executing the program, it gets loaded into memory. Some RAM gets allocated to it, and then the CPU starts executing that program. Okay. The question is, how are we going to actually allocate memory, and how is the CPU going to execute whatever is in memory? How does it fetch it, and so on. Okay. So some terminology to keep in mind. Okay, that's a very simple picture of RAM that's laid out logically with 3 processes A, B, and C. Okay, and then the RAM, basically the addresses go from 0 to 2400 in this case. Okay. So we'll use the term segment to define the term segment as any chunk of memory you allocate to a process. Okay. And there are 2 concepts you really need to understand for you to understand any memory management scheme. That's physical address and virtual address. Okay. Physical address is actually the address of a location in RAM. Okay. So when you have RAM that goes from 0 to 2400, addresses will go 0, 1, 2, and that's going to address the 0th word and the first word and the second word and so on. Okay. What's a virtual address? Anyone remember anything? Memory management? Yes, James.
Essentially, it's just an address that theoretically could be the same address number as the physical address, but it's just an abstraction away that the program thinks only has access to.
Right. So the virtual address is essentially an address generated by a process, okay, and it is an address relative to the start of that process. Okay. In some sense, it's a relative address. Okay. So when a process says address 5, it's saying the 5th word from where that process starts. Okay. That's what we mean by virtual address. Right. Now clearly a virtual address will map to a physical address based on where that process is actually loaded. Right. So for process A in this case, the 5th word will actually have, since the process started at 400, is going to have address 405. Okay. And for this other process, maybe B, which starts at 2000, okay, its 5th word will, the virtual address is still 5, the physical address is different. Okay, 2005. Right. Now what this very simple example is going to show you is that the memory manager has, not the memory manager, in this case it's the hardware, has to do this translation on the fly when the process is executing, and we'll see different schemes require different ways to make this translation work. Okay. So every time a program executes, is essentially going to generate a virtual address, and then you have to translate that to a physical address. Okay. And the reason is not the reason. The question is why. Okay. Why do you actually have to generate a virtual address? Why could the program not generate a physical address? Okay. Why are we saying that when you have executable code or assembly code or machine code, all the addresses it is generating in an instruction where an array is stored, where a variable is stored, they are all virtual addresses. Why couldn't they be physical addresses? Yes?
They were loaded into a different address than the one they expected they would be getting.
Right. Okay, so that has some issues with where you load the process. Anyone have anything else? Yes?
There's a security concern, like if you know that it will always be in certain places of memory.
Okay, so it's a security concern as well. Right, so as you can imagine, when you write your code, okay, the programmer has no concept of where that program will ever be loaded in memory. Every time you execute it, it could be loaded in a different part of memory. Okay. So you cannot possibly know when you write your code, first you don't write assembly code, but assume that you did. Okay, you have no idea where the OS is going to load your program. Okay. Neither does the compiler, because you write source code, but the compiler generates machine code for you. The compiler doesn't know where the OS is going to load. Okay. So when you execute, not when you execute, when you generate this executable, you don't know where the process is going to run in memory. So you cannot possibly generate physical addresses. So what you always do is you say, I know where the relative to the start of this program, where which part of this process I am trying to access. So I can always generate relative addresses, always relative to the start. Okay. And then depending on where the OS chooses to load this process, you can actually figure out what virtual address maps to what physical address at runtime. So this translation is actually going to happen at runtime. Sometimes you can do this at load time, but you cannot do this at compile time unless you have a uniprogram system. In a uniprogram system, you have only one process executing at any time. You can make an assumption that that process is always loaded at address 0, physical address 0. So in this case, virtual addresses and physical addresses will be the same because the start of the process is address 0. Okay. As the only time you can actually generate physical addresses, but most systems are not uniprogram systems, they are multi-program systems. They run multiple processes, they have concurrency, so you can't actually make that assumption in practice. Okay. So this is uniprogramming, which says only one process is executing and you can always load that process at address 0. So in this case, your physical addresses are the same as virtual addresses. So you are effectively generating physical addresses. But that's the only time you can do this at compile time, okay, but not in a multi-program system. Okay. Now, in a multi-program system, since multiple processes are sharing the same RAM, we need some nice properties. Okay. The first one is transparency. Okay. The program should run the same regardless of where it's loaded in memory. Okay. Program shouldn't care where it's loaded in. OS decides and the program just process just executes as is. Okay. Then we want safety, which is one process should not be able to get access to the memory region belonging to another process. Okay. Otherwise, you can essentially go and trample some other process's memory. Okay. You can read sensitive things that are in that. Okay. Third one is efficiency. Because the physical to virtual address translation is happening at runtime, you want that to be done efficiently. And we'll see some schemes that are not as efficient and see how to make them better. Okay. So now let's start with the first one, which is relocation. Okay. So what relocation simply says is you take a process, okay, then allocate it some chunk of memory, which could be arbitrary. Okay, now somehow you have to take its virtual address and translate it to a physical address. So what kind of techniques could you use to do this? How are you going to do this translation of virtual addresses to physical addresses? In particular, let's take that example that's shown there, which is that you have a new process C that is starting up. You decided to load it at address number 900. Okay. So how are we going to take its virtual addresses and do a translation to physical addresses? Yes.
You could have like a base buffer that you load with like the start of the physical memory address, and then add it to each virtual address.
Yes. So I think there are two schemes you have to keep in mind. Okay. First is called static, the other is dynamic. Okay. In static relocation, what you are going to do is the loader. The loader is the program that's loading your executable from disk to memory. Okay. The loader is actually going to scan through your assembly instruction, okay, take every virtual address that it finds, okay, and adds to that virtual address the start address of that process. Okay. And that gives you a physical address. Okay. So this is done at load time. This is called static relocation. So in this case, since C is being loaded at 900, okay, you are going to scan through all the assembly instructions or machine code in C. Every time you see a virtual address, you are going to essentially add 900 to it, and then essentially that gives you a physical address. So now all assembly instructions or machine code actually has physical address built in. Okay. So you essentially went and modified your binary to include the actual address where the process is loaded. Okay. Now that's not very good, because if you happen to move that process later, all your addresses are incorrect. Okay. And why would you want to move a process? To make room for another one. So what if A, which is now sitting between B and C, starts essentially allocating more memory on its heap and it needs more space? Because you can of course do malloc or new or whatever else you do in your program, allocate new memory. The process grows, there isn't room for it to grow, you might have to move a process to make room. Okay, so in this case, all your work that you did has to be undone or redone. Okay. So, a better approach, which is the approach that was actually mentioned, is to actually use hardware to do this for us. Okay. Let the process generate virtual addresses. Okay. We will have some runtime hardware that will allow us to generate physical addresses, and that runtime hardware essentially has what's called a base register or a relocation register that holds the starting address. So, you take every address that comes in, you have an adder that sums them together, and you get a physical address. Okay. And because this is being done in hardware, it's going to be fast. You're not executing code to do this. You actually have an adder and a register, and you're just adding. Okay. You will see that in that picture, there's a second register called a limit register. Anyone remember what that is? Yes.
It's like the highest address that the process can go to, and anything past that's like out of its memory region.
Okay. So, the limit register is going to hold the ending address of that process. Okay. And you are going to have a comparator there, which says if you generate an address that exceeds the limit register, that's an invalid address, because that's actually exceeding your allocated region of memory. It overflows into some other process's memory. So, you are going to disallow that. Okay, so, you will see that says that you are going to create a trap, you are going to get an addressing error. Okay, so, you are going to do a range check to make sure your addresses are valid, and so you are going to use an adder to generate a physical address, you are going to use a comparator to compare it. Okay. Yes.
How does the process decide how much memory is allocated?
Okay. Question: how does the process decide how much memory it's allocated? The process typically will not decide that. It's the job of the OS to decide how much memory to allocate. Typically, you will have enough memory to hold the code for the process as the text segment, and then you allocate some extra memory to hold the stack and the heap. Okay. And we will talk about memory allocation schemes in just a moment that will clarify some of these issues, because you don't know how much the process might grow over time and things of that sort. Yes.
So, for static relocation, you said that it might have to move if it
Yes.
requires more memory, but on the slide it says the OS cannot move it.
Right. So, okay, I don't know which. Okay, static relocation, you don't want the OS to move it without changing the addresses. I think if you just move it, it will be incorrect. If you move it, you have to actually change the address. So, you don't want the OS to do something without changing the address. That's what it means. Now, in a dynamic relocation scheme, it should be clear that you can move the process anywhere, because all you need to do is change those two register values and everything else remains the same. Okay? All right. So, we did dynamic relocation. We will skip the advantages, disadvantages. Okay, it should be clear that this is transparency is achieved, because the process doesn't know that the hardware is doing all this translation. It's just happening under the hoods. There's safety, because you are doing this range check to make sure you cannot access some other process's memory. It's efficient because you are doing all this translation using special hardware. Okay, that's built into the CPU. Okay. So, that is relocation. Okay. Now, let us go back to memory allocation. There was a question that was asked, how do you allocate how much memory to give to a process? Okay. Now, let us assume that for every process you decide you will allocate enough memory to hold the text segment, which is the code, okay, which could be of arbitrary size, okay, some memory for the stack, and you might just estimate that it needs some initial amount of memory for the heap, which can grow over time. Okay. That gives you some estimate of how much the process needs when it starts. Okay. So, when you load a new process, you have to actually scan your RAM to see where that process can fit. Okay. What is shown in that picture is a contiguous allocation scheme, where that entire process is put in one contiguous region in RAM. Okay. So, in this case, you have A, B, and C, then you see that B is actually terminated. So, you create the gray region indicates that RAM is unallocated. Okay, anything that's not gray means it's allocated. So, then C arrives, or not C, D arrives, and it's actually put where B used to reside. Okay. So, over time processes will come and go. So, you got to keep track of all unallocated regions of memory, and then whenever a new process arrives, you have to find a region that's large enough to hold it. Okay. What are some schemes you can use to do this? How are you going to figure out where to put a process? Yes. Okay, so you can use techniques that are called first fit, best fit, last fit. So what you have to essentially do, and by the way, this is what Minix does. Okay, this is the most rudimentary approach, and you will see that when you do memory management lab, that this is essentially what Minix is doing. You have to essentially keep a list of what are called holes. Okay, a hole is essentially those list of those gray regions. Those are unallocated or free regions in RAM. Okay, so you got to keep a list of holes, and then you say, here's a new process, it needs 10 megabytes. Right? So then you scan through your list of holes and find one that is going to be enough to accommodate that process. Okay, and then you will basically put it there. Now there are different policies that you can use, as was mentioned. In first fit, you just scan it and find the first one. In the best fit, you find the smallest hole that's big enough to hold that process. Okay? And in worst fit, you are going to find the biggest hole that's big enough to hold that process. Okay. There are many policies. Okay, and I think, as I said, you can use either one. Okay. Most of the OSs that use this contiguous memory allocation systems, not a whole lot of them anymore, but there are ones like Minix that do, will use the best fit because it basically gives you good properties. Okay. What are those properties? What might be some problems with this approach? Let me ask you that first. Yes. Okay, it's like fragmentation. What is fragmentation? Yes.
There's two kinds. There's external and internal. External is when the holes are sort of too small to be used for a process.
Okay.
And then internal is when you use paging, when you have
Okay.
memory that's not used.
Okay. So you're right, except what you said towards the end. I will modify that just a little bit. Okay, let me show you an example. Okay. So here is an example where if you take all those gray regions and you sum them up, you will say I have X amounts of unallocated memory. Okay, I have 100 megabytes unallocated. Okay. New process comes, in this case it needs 600 bytes. Okay. You are going to scan through all of those gray regions and find one that's big enough to hold a 600 byte process. You don't find any, because all of them are smaller than 600. In the aggregate, enough unallocated RAM, but there's no hole that's big enough. Okay, so that's called fragmentation. It's called specifically it's called external fragmentation. Okay. So as you have processes that come and go, your memory is going to get fragmented between allocated processes and small holes that sit between two processes. Okay, so that means essentially you will have lots of regions that cannot be used because they are not big enough to hold a process. Okay. Now the way this is addressed, eventually when you have lots of fragmentation, you are going to do compaction, which means you take all of those processes and you move them up. Right. So if you essentially do this, you are going to move D and C up, then you have one big gray region again which has all the unallocated RAM, then you can fit a process that came in and asked for the 600. Okay. This is why you might actually have to move a process in dynamic relocation. Okay. So that's external fragmentation. Now internal fragmentation is a slightly different concept. Okay. So this one says if I need X amount of memory for a process, okay, I am going to allocate it something slightly bigger than X. Okay. That means the process has been given memory that it is not using, and that small region that it's not using is called internal fragmentation. Okay. And here's an example which says I need a process that wants 8864 bytes of RAM. Okay. I allocate it a hole that's 8848 bytes, which is 2 bytes bigger. Okay. But if I gave it exactly what it wanted, I am left with a 2 byte hole. Okay, which is completely useless. I cannot allocate 2 bytes to any process. So I might as well allocate it that entire region and not have to deal with this small fragmented piece of memory, because it also makes my list of holes also bigger. That list is bigger, so I have to scan more entries to figure out which process goes where and so on. So it reduces the efficiency of the memory allocator. Okay, so that's internal fragmentation. We will come back to what you said about paging also as internal fragmentation a little bit, but the concept is not directly related to paging. It's just saying you allocate more memory to a process than it needs. Okay. Any questions on any of this? You're going to pick up speed and then go through lots of things quickly. Yes.
The
Okay. So, question is, does the fragmentation happen, when does it happen? So, if you have a machine that has not been rebooted in a while, there have been processes that have started, terminated and so on. Over time you are going to get a fragmented RAM. Okay. That is when you are going to see this fragmentation. Okay. We will see schemes that do not have any fragmentation at all, because you do not want to deal with this to begin with. So, this is a very rudimentary scheme. Okay. Minix uses it, but there is a toy operating system in educational, not but there are also embedded OSs that use it, okay, because other schemes have more do more sophisticated things, but they come at a cost.
Windows also has this fragmentation option where you should do that every now and then.
Okay. So, you are asking, so there are two types of fragmentation, this fragmentation of memory and fragmentation of disk. Okay. So, we are, when you talk about Windows or any other machine, that is we are talking about disk fragment. The same thing can happen on disk, where files get created and deleted. Okay. So, that is a different concept, that is still fragmentation, but slightly different from memory. Okay. Yes.
How often do we do compaction? Like, is it only when we find a process which cannot fit into it, or how does an OS decide exactly?
Okay. Question, how do you do compaction? As you can imagine, there are a number of policies, right. So, compaction is essentially garbage collection. Java will do garbage collection, is essentially doing similar stuff, is taking memory back and trying to reclaim unused memory in some way, right. How often to do it depends on the policy that the OS implements. You could say, I will wait until there is a process that comes in and you don't, it cannot fit any hole, at that point I trigger compaction, that is completely on demand. Okay. Or you can say, every hour I am going to do it, or every so often, every time t units I run compaction, that is proactive compaction. All of these policies are possible, because it comes with a cost. If you do it too frequently and you do not need it, you wasted some extra work by copying memory that did not need to be copied, because moving a process involves memory copy. So, you are copying it from one region to another, that comes at a cost. Okay. Yes.
Is the memory manager like constantly active and looking for these opportunities? Like when does it invoke? Like in some lines of code, right? Like when are these instructions being run? Is it time based?
Right. So, question is, when is it being invoked? So the memory manager is invoked for numerous reasons. One is a new process comes, you say allocate memory. Process gets terminated, free up memory. Okay. Process does not fit in memory, run compaction. Right. So, all of these are going to be on demand, only when something happens. Right. So, the other option I was mentioning was you do it proactively, which means you can run the compaction method every so often. You can set up parameters and run it every hour. In that case, even though nothing may be happening, you will still run the memory manager, do compaction. Okay. All right. So, now let us move on to the next technique, which is paging. Okay. So, the problem with contiguous allocation is going to give us fragmentation. I think that is a bad problem to have. So, there are other approaches that just do away with that problem altogether. Okay. The way you are going to do this is, rather than doing contiguous memory allocation, you are going to partition memory into fixed size units, okay, and say which are called frames. Okay. You are going to take each process and also partition into the same fixed size units, which you are going to call pages. Yes, pages are basically chunks of a process, frames are chunks of RAM. Okay. Both are of the same size, and our idea here is going to be any page can be allocated to any unused frame. Okay. Process does not need to be contiguous in memory anymore. You are just going to allocate essentially a page to any frame, okay, which is shown there. Okay. The first picture, or the picture to your left, is essentially a process. Okay. Rather than allocating an entire chunk, we partitioned it into fixed size frames, or not frames, pages in this case, which are labeled A0 through A5. Okay. And now we say any of those pages can be put anywhere. They no longer have to be contiguous. So, those arrows tell you where each of those pages is loaded in memory. Okay. So, the process no longer sits contiguously in memory, pieces of it are spread across memory. Okay. So, this gets rid of the fragmentation problem, because there will not be any fragmentation by definition, because you just need any unused frame can be allocated to any process. So, you will not waste any memory anymore. Okay. Is that clear? Okay. So now the other question is, what is the memory hardware have to do to allow such a process to execute? Because the process, remember, is still generating virtual addresses. Okay? When you allocated memory contiguously, all you needed was the start address of that process. And then you could take a virtual address 5, you add the base address, and you got the physical address. Now the start address doesn't make any sense because there is no start address. The process is not loaded in memory anymore contiguously. Okay, so how are we going to do that address translation? Yes. Okay, you have a table. What does the table do?
Has the mapping between the processes in each of the pages.
Okay, so I should be clear. The OS needs to know where the process is loaded in memory. So all of those arrows tell you the mapping between a page to a frame. Okay, the OS needs to track that information. Okay, this is done through a data structure called a page table. Page table is implemented in hardware. Okay, actually not necessarily in hardware, it could be implemented in software, but it's a table that the OS maintains. Okay, so the table is going to essentially have this mapping between. So that's the page table there, which is shown at the bottom. For each page, you are going to keep the frame number. Okay, so page 1 is kept in frame 5, page 2 is kept in frame 7. Okay, they don't have to be contiguous. Okay. So now if you have a virtual address, you have to figure out how to do the translation from a virtual to physical address. Okay. How are you going to do that? Okay, it's shown in the picture there, but what is the concept? Yes.
You basically take the address, basically modulo by the page size, so you have whatever, how far in that page you are, and then just add it to whatever the frame address is.
Okay. So essentially what you are going to do is, given a virtual address, which is simply an offset from the beginning of that process, you are going to say which page is that address in. Is it the 0th page, the first page? We know the page sizes are fixed. Let's say there are 4K pages. Okay. So the first 4096 addresses are going to be in the first page. The next 4096 addresses in the second page, and so on. Okay. So given an address, you are going to first divide by the page size, and that is going to give you the page number it resides in. Okay, so you are going to say it is in the ith page. Then you are going to index the page table and say where is the ith page stored in RAM, because the page table is going to give you a mapping from page number to frame number. Okay, so in this case you will see that you essentially indexed into the p says at this address of the frame, the start address of the frame. Okay. So you take the start address of the frame and then you essentially add the offset, which gives you a physical address. Is that clear? Okay. Now the way this is actually done in hardware is that page sizes, if you make them some exponent of 2, okay, that basically then tells us that these many bits of that address are going to represent the page number, and the remaining bits are going to be the offset into the page. This only works if your page size is some exponent of 2, which means they can be 2 to the power something, 4096 or 8192 or what, some exponent of 2. If you do that, you can essentially look at the binary representation of that address and pick the most significant bit, some number of them. Okay, that essentially gives you the page number. Okay, and then the remaining least significant bits is going to give you an offset into the page. So all you are doing in this case is essentially taking these bits here. Okay, these bits, that binary string represents the page number. You index here, that gives you a frame number. You replace the page number with the frame number, and then the offset that essentially gives you that bit binary representation is essentially going to give you a physical address in memory. Okay. So all of this can be done efficiently in hardware because you're going to keep all of this. Yes, question.
So isn't the page table stored in memory because like hardware means like we have only a certain mappings, right?
Yes.
So we are bound by the hardware's constraints.
Can you repeat your question? I'm not following what you say.
If the number of process increases, the mappings will increase.
Yes.
But the hardware might be constrained to store all the mappings.
Yes. So the question is, what are the hardware constraints? So first thing is every process is going to have its own page table. It's not that there's one page table for the entire system. This is a per process data structure, okay, which the OS has to track. Okay. Now, the OS, if you are assuming that all processes are resident in RAM at all times, okay, your OS is essentially going to have some limits on how many processes can be loaded, because all the processes have to fit in RAM. Okay. We will see how to relax that assumption in a few minutes when you talk about demand paging. So the question you are asking has nothing to do with page tables. It is simply saying if a RAM is of a certain size, okay, you are going to be limited by how many processes can execute, because if you have 16 GB RAM on your machine, the total size of all processes cannot exceed 16 GB. If you try to exceed that, you are going to get an error, okay, unless you do something different from a simple paging approach. Okay. So that's the first thing I want to mention. Second thing that you asked is page tables are stored in memory. Okay. So that table that you see there is going to be a piece of memory that's maintained by the OS. Okay. Now that has an important implication on the efficiency of paging. Okay. So what is that implication? Why do we care if the page table is stored in memory? Yes.
We have to know where to get the page table from. Convert that page tables physical memory to virtual memory, and then if it's in the memory, like you might have to bring it to cache.
Okay, so what does all that do? Yes. Okay, it increases access time. Right. So think of an instruction. Let's say you have a move instruction. Okay, move instruction simply says take this register and put it in this memory region. That's a memory address. Okay. Now to figure out, that's a virtual address. First, before you execute this instruction, you have to do a translation from that virtual address to memory address. Right. Now to do that translation, you have to go to the page table. Okay. Page table is itself stored in RAM. Okay. So what was one memory access for this instruction has essentially become two memory accesses, because you have got to access the page table to figure out where that address is, and then you can execute that instruction which actually goes and looks up that memory region. Okay. So effectively slowed down memory accesses by a factor of 2. Right. So essentially you are going to cut all the speeds, execution speed of all the memory instructions by factor of 2. You are going to get a big slowdown. Okay. You don't want that. So what can you do? Yes. TLC, close enough. TLB. Yes. Right. So you are going to add some hardware. So I'm going to skip all these examples that make you mechanically do this translation and just show you how to make paging efficient, which is you are going to essentially put a cache for the page table. That cache is implemented in hardware. It's a very fast lookup table. For a TLB, the name aside, all that is doing is it's storing recently accessed entries of that page table. This is the real page table. Okay. That's a cache for the page table. Okay. Accessing that cache is much faster than accessing the page table. So you take the most recently accessed entries of that page table, put it in the cache. Okay. If you have locality of reference, which means that process accesses similar addresses or the same addresses again, you are going to essentially have those entries cached, the page table entries cached. So the lookup of the page table is sped up. You are no longer going to get a factor of 2 slowdown, because accessing the page table does not need a full memory access. It only needs a cache access. Okay. Whenever you have a TLB miss, you are still going to have to go to the page table, fetch that entry, put it in the TLB. So those instructions will still be slowed down by a factor of 2. Okay, but we'll assume that TLB misses are rare because of locality of reference, okay, how processes execute. So most of the time the entries are already in the TLB. So your page tables are not going to be accessed in RAM. Page table entries are going to be accessed from the TLB. That makes paging efficient. Okay. Otherwise, this is a good scheme to get rid of fragmentation, but you basically got a factor of 2 slowed down. You slowed down your execution of the process by a factor of 2. Okay. That's too much of a price to pay. Okay. So you throw in some hardware, which in this case is a TLB. Okay. That's going to speed things up. Is that clear? Okay. So there are some details there that I'm going to ignore. You should know what a TLB is. Yeah, so there's some example here which says, yes, you have a question.
Just having a doubt about the page table. So when a process requires a certain memory, like we look at the page table, that's a TLB mess.
Yes.
Like how do we get the address for the page table itself? How do we know where it is stored?
Okay, question, how do you know the address of the page table? So the address of the page table is going to be tracked by the OS. Remember I said 2 or 3 classes ago that there's a process table that stores everything that the OS needs to know. Okay? One of the things it needs to know is where the page table is stored. So the address of the page table is stored in the process table. So if you know the process ID, you go to the process table, look up the entry in the process table that has a pointer to the page table. Okay? Oh, yes.
The size of pages, is it a design decision? Is it different in
Okay. Question is size of pages. So that's a hardware level decision typically. Okay. So typically many of these, because the TLB is a hardware construct and the number of bits for the page is already decided in the TLB, most of this is actually going to be designed at a hardware level. So most of these machines will have a 4K or a 8K page table. I mean, sorry, page size, not page table. Right. So once you use that, then your OS is somewhat bound. OS can use something bigger than that, but though typically OSs will just go with whatever the hardware. You cannot do anything smaller because that's the smallest unit of RAM that the TLB understands. Okay. Anything else? Okay. So we are going to look at the next scheme quickly, which is okay. So I do want to say one thing here before I move on. So the 2 expressions there tell you the efficiency of paging without having a TLB and the efficiency of paging with a TLB. Okay, you will see that EMA is basically stands for effective memory access time. Without a TLB, you will see that effective memory access time is 2 times the time to access RAM, which is 2 times MA, memory access time. Okay. Once you put in a TLB, you will essentially say if the probability of a TLB hit is P. Okay, so essentially memory access time is time to look up TLB plus time to access memory. Okay, it's TLB plus MA. Okay. And whenever you have a TLB miss, which is probability 1 minus P, you are essentially going to get TLB plus 2 MA. You will go to the TLB, see it's a miss, go to the page table, then go to RAM and access memory. Okay. So that's the kind of analysis that shows you. So most of the time you are going to, if P is high, this expression will be close to the first quantity, which is much better than twice of MA. Okay. That makes it more efficient. Okay. All right. So next up is I'm going to skip that you have to save the TLB and all of that on context switches and talk about segmentation. Okay. So the next scheme is called segmentation, and this scheme actually thinks about allocating memory that relates to how processes view memory. Okay. So if you remember the picture I had drawn some time ago, okay, which was if you look at the logical layout of a process, you have essentially a text segment, you have a stack that grows upwards, you have a heap that grows downwards. Okay. So as far as processes are concerned and compilers, when it generates machine code, it thinks of a logical view of the process where the process memory is divided into segments. The text segments holds code for the process. The heap segment stores dynamically allocated data structure. The stack stores essentially local variables and things of that sort. Okay. That's the process view. Okay. This process view has no concept of what a page is. Okay. Page is something that the OS and the hardware put in place. The processes didn't care about pages at all. Processes basically say go to the text segment, get this instruction executor, go to the stack, pull up that variable and things of that sort. So this is how the process thinks it's laid out in memory. Okay. What segmentation does is it allocates memory by looking at the processes view of memory rather than some other approach that we have looked at, which is either contiguous or paging based. Okay, so essentially what you are going to do here is if you have RAM, okay, and this process essentially has 3 segments, text segment, stack and heap, you are going to say let's allocate some memory for the text segment, and you are going to say here is the text segment. Okay, and say let's allocate some memory for the stack segment. So you are going to basically put the stack here, and can and then heap. So you are going to take each of the segments of a process and allocate it contiguously, not that you allocate the entire process contiguously. Okay. In contiguous memory allocation, you took this entire chunk and said let's put it in one place in memory. Okay. Here you are saying let's take the text segment, let's put it contiguously. Let's take the stack, put it contiguously, and then the heap, and so on. Okay. So this is called segmentation. It is somewhere between contiguous and paging. Basically, just things are going to be larger page because this is the entire all of the code. This is all of the heap, and so on and so forth. Okay. So now the addressing of the process is different from paging, where you are going to take a virtual address and say I am going to number this segment. Let's say I go, this is segment 0, segment 1, segment 2, and so on. So to generate an address, I am going to ask which segment is it in, okay, and then what is the offset of that address relative to the start of the segment, right? Because if this is stored contiguously, I can say segment 0, which is a text segment, the 5th word. Okay, that's by offset 5 from the top. Okay, that's how I'm going to address this. So there will be a segment number and an offset, which is the address of the start of that segment. So you are going to essentially do this translation on the fly. Okay, and to do this, you need another data structure called the segment table, not a page table, a segment table. Okay, each entry of the segment table is going to have a base address, which is the start address of where that segment is loaded. Okay, and then it's going to have a limit register that says how large that segment is. Okay, so you will see that segment table entries are essentially base limit pairs. Okay, so to do address translation, you take a virtual address, you find the segment that is stored in, you index the segment table, okay, with that segment ID, and then you find the base, take the base and the offset, you sum them. Okay. You still need the comparator to figure out whether you are exceeding the limit register. Okay. If you exceed it, you essentially get a trap. This is called a segmentation fault. Okay. Typically, if you crash a process, you get an error called a segmentation fault. Essentially, it failed that check because you are addressing something that's out of bounds from that segment's valid memory addresses. Okay. Now, you can see that this is going to essentially go back to contiguous memory allocation, except that you are allocating contiguous memory for segments rather than the whole process. So you are going to be back with fragmentation, right? Because the same thing, you are going to have holes and you are going to put segments in holes, and you are going to have segmentation, or not segment, fragmentation again, and so on and so forth. Okay? So what can you do to get rid of fragmentation of segments? Okay. Okay. So basically, what you could do is essentially combine segmentation and paging. Okay. The advantage of segmentation is it corresponds to the process's view of what its memory looks like. Because the process doesn't care about pages. It says this is the text segment, which is code, the heap, stack. So that's how the process views it. Okay. And the advantage of paging is because you are allocating memory in fixed size chunks, you have no fragmentation. You can put any part of that process anywhere in RAM and so on. Okay. So you want to combine the process view and the OS view of memory. That gives you an approach called segmented paging, okay, which most sophisticated OSs are going to be using. They don't do any of what we talked about. They essentially do this combined approach, which combines segmentation and paging. So essentially, that's what it looks like. Okay. So you are going to have segments. Each segment is going to be partitioned into fixed size chunks called pages. Okay. And then you are going to put any page of a segment anywhere in memory. Okay. So now the address translation in this case, this is a good approach because it combines the segmentation view and the OS view, but the address translation is going to be a lot more complicated, okay, because you need multiple data structures in this case. First, you need a segment table. Okay. Now, in this case, the segment table is not pointing to where the segment is stored in memory, because segment is no longer stored contiguously in memory. It's paged. Okay. So every segment now has a page table. Just as previously every process had a page table, every segment looks like a little process which is paged. So every segment has its own page table. So the text segment will have a page table, the stack will have a page table, the heap will have a page table, and so on. Okay. So the segment table in this case is going to point to the page table for that segment. Okay. So two levels of indirection. Given a virtual address, you say which segment is this? Is this the stack? Is this the heap? Is this the text segment? You go and look up the segment table entry. That gives you the page table for that segment. So now you say, okay, now I know this is the heap. What offset am I looking for? And on which page is that offset in? Then you look up the page table, find the page number, translate that to a frame number, and then that's going to give you the physical address together with the offset. Okay. So you will see that now there are multiple tables, segment tables and multiple page tables for each process, one per segment. Okay. And there are two levels of lookup to be done. Okay. If the segment table is in RAM, the page table is in RAM, factor of 3 slow down. Okay. You are making things more sophisticated, but slowing your machine down tremendously. Okay. You do not want that to happen. So you are again going to add some hardware to make all of this fast. Okay. So you can say the segment table can actually be stored in registers, because there are not that many segments. If you have 3 segments, you need 6 registers. Right. So you can put them in registers, and that will be really fast because it's the fastest memory we have at our disposal. For page tables, we can still use the TLB. That option has not gone away. Okay. So in the fast path, if there are no misses of the segment table and all of that, you are going to do one register access, or in this case 2, the base and limit registers, to get the segment table information, one TLB lookup to get the page table information, and then you are done. Then you go and access the memory. So that's not going to give you much of a slowdown. Okay. In the slow path, you are going to have factor of 3 slowdown, and you hope that that really happens very rarely. Otherwise, you are going to get a big slowdown in your execution speeds. Is that clear? Okay, next question. Okay, so what advantage does segmented paging have over normal paging? In segmented paging, you are preserving the segmented view of a process where the process can still think of addresses as the 5th address in the text segment, or the 3rd word in the stack segment, and the 5th word in the heap, and so on, because you still have the segment view of that process. Okay. But because you do not want fragmentation, you take each segment and you page them. That way you do not get fragmentation. So you preserve, so the OS likes paging because there is no fragmentation. The process prefers segment view because that is how it is laid out. So you combine the two. Okay. So your virtual addresses will still be a segment ID and some offset within the segment. You take that offset and you page that, so then you do a page table lookup and get the actual address. Okay. Yes, question.
Why exactly do you need the segment table though? Like, let's say if a process already knows where its stack is in the current time, it knows the address of that, so it can look it up in a page table. So what's the point of having the segment table then?
The segment tables are simply pointers to the page tables, right? So each of these will have a page table which are going to point to pages, right? So you used to pointer to a page table to be kept somewhere. Even in paging, you needed to know where the page table was stored, right? Typically, you have actually have a register to store. I sort of glossed over that. You had a register that said here is where the page table is stored. Okay, so this is that register. So think of a paging as just a process with one segment. You still needed to store the start address of the page table, which is stored in register. In segmentation, all you said was I can have multiple segments instead of one. So there's several registers that tell you where the page tables for each of those segments are stored. That's all. And then everything you said makes sense because all that information is in the page table. Okay, so this is simply the pointer to a page table. Anything else? Okay, last scheme is, again I'm going to skip all these examples. Oh, I do want to say one thing, which is shared segments and shared pages. Okay, this is actually important because I didn't say about memory sharing. Okay. Now, OSs will try to optimize the use of RAM by trying to not duplicate things in RAM. Okay. So suppose that you have 2 Python programs running in RAM. Okay. Should you load the Python interpreter twice? It's the same interpreter, it's going to waste RAM. Okay. Or maybe a C program. Okay. It basically uses libc as its main library. Okay. Should you actually load that library multiple times? It's going to waste RAM because the same region is stored multiple times. Okay. So what you could instead do is you can say now you can have additional segments which are essentially shared segments. So you can say I have a libc library segment. Okay. And that segment can now be shared across multiple processes. So you only have one copy of it in RAM at any time. Okay. Because it's exactly the same library. Rather than loading it multiple times, you essentially load it once here. Well, it's actually paged, but let's assume it's stored there. There are 2 processes that essentially need to access libc. Both of the segment table entries are going to point to the same page table that is essentially going to be pointing to libc. Okay. So you can share memory very easily in segmentation, because all you are going to do to share a segment is essentially that register is going to point to the same page table for that segment. Okay. And so you can do shared libraries very easily. Okay. Sharing of libraries is something that most OSs will use as a memory optimization to prevent duplicate pieces of duplicate libraries being loaded in RAM. Okay. This saves you quite a bit of RAM space, because if you have 10 processes, they use the same library, you only have to have one copy instead of having 10 copies. Okay. So sharing of memory is very easy in segmentation. You can take that entire segment, okay, and share it. You can also share pages. Okay. So if you wanted to share more granular information, you could take a page and you could have 2 processes, their page tables or entries are pointing to the same frame. That's also possible. Okay. But you can see now, if you have a segmented view, you can take a large chunk region of memory, which is a segment, and then share them by just pointing to the same page. It simplified things dramatically. If you had to do this at a paging level, lots of entries would have to be replicated in the page table, or some entries of both page tables are pointing to the same frames. It's a little more complicated. This simplifies things dramatically. Okay. So you can, when you have paging and when you have segmentation, you can share memory. Okay. And segmentation is used to share libraries. Paging you can use to have actual shared memory regions. You can create these memory regions that 2 processes share. Because by default, 2 processes do not share memory. That was our default assumption. You cannot touch some other process's memory. But when you need to, you can create the special regions called shared memory regions. And then the way they are going to get shared is either at a segment level or at the page level. Okay. So these are some advanced things that you will have to keep in mind when you do the assignments and things of that sort. Okay. So that's sharing. Then the last concept I'm going to talk about is demand paging. Okay. So demand paging is essentially going to take our segmented paging scheme and generalize it and say we are no longer going to be bound by size of RAM. You can start a process that could be of arbitrary size. The size of a single process can exceed the size of RAM, and I still want to be able to execute that process. Okay. So how are we going to do it? We are not going to load the entire process in RAM at any given time. Okay, because you do not have enough RAM by definition to hold large processes or some collection of large processes. Okay. So we are going to use a technique which is called the working set. Okay. Working set of a process is the set of pages that it's currently accessing. Okay. We are going to assume that the working set is the set of memory pages that it's accessing, and keeping just the working set in memory is going to give us reasonable performance. Okay. It's an important assumption. It depends on processes exploiting locality of reference. Okay. If process memory accesses were random, this would never work, because that would say all accesses are random. I don't know which page it's going to access next, so then I cannot figure out which pages to keep in memory. Okay. So if I only want to keep a subset of a process's pages or segments in memory, I need to make some assumption saying that there are some pages that it accesses frequently. Those are the ones I'm going to keep in memory. Okay. That's called the working set. Okay. Everything else is kept on disk. Okay. So, you will essentially have a region of disk called swap space. Okay. When you start a process, you will actually copy most of its content to swap space. You will only allocate a small amount of memory to that process, not equal to the size of that process, but something much smaller which is equal to the working set size, and then you only keep a subset of it in memory. Okay. Now, eventually the working set is not going to be static, it is changing over time depending on what you are executing. So, whenever you execute an instruction that accesses a page that is not stored in memory, you are going to get a page fault. Okay. Page fault says I access RAM that is not currently, I access page that is not currently in RAM. So, I have to go to disk and fetch that page. So, you are going to have a significant slowdown where you are going to have to go get a disk access and fetch that page into RAM. Okay. And you are going to update the page table. Okay. Now, this only works because locality of reference will give us a property where page faults are going to be rare. If page faults are going to be frequent, your process is now going to execute at speed of disk, not 2 times slower than memory, million times slower than memory, because disk is several orders of magnitude slower than RAM, and your process will basically not execute at that point, it will slow down significantly. Okay. So, this is called demand paging. Demand paging says we are only going to bring in pages on demand depending on what the process is executing. We will keep the working set in memory, everything else is stored on disk. Okay. And there are quite a bit of things you have to do to get demand paging right. One of which is what is the working set of a process, how do you decide that? Is it 10 pages, 100 pages, 1000 pages? Okay. It will depend on the process. Okay. And that working set will change over time, the size of the working set will change over time. You have to track that well and make sure you always keep the working set in memory and so on. Okay. So, now your memory management is going to get more sophisticated and also more complicated, because you want to have good performance. You want to ensure that page faults that as working set you are going to out. And then if you are bringing a page from disk to RAM, you have to evict something from RAM to disk, okay, because you have to make some space for that page. Okay. Which one will you evict? Okay. So, that is called page replacement. Okay. You might have, if you remember your OS class, you might have actually encountered these approaches like that is your, I will come back to this picture, but you would have, you might remember this these techniques like FIFO and MIN and LRU and so on. Okay, least recently used. So, these policies says if you have a page fault to bring in a page, it tells you which page to evict. Okay. It still does not tell us what the working set is, but it does tell us what to do if you have to make room for a new page. Okay. So, all of these are going to significantly complicate memory management. Okay. Most general purpose OSs will do demand paging and they will use segmented paging. For whatever is in RAM, you use segments and page tables, but not everything is in RAM, some things are on disk. So, you are going to bring it on demand. Okay. So, that is basically going to combine keeping parts of a process in RAM and parts on disk with taking whatever is in RAM and then having segmentation and paging combined. Okay. So, you will see that that is going to significantly complicate your memory management. Okay. Fortunately, from a lab perspective, Minix does not do any of this. Okay. It does this as the simplest thing, which is does a little bit of paging and it does some contiguous memory allocation. Okay. So, and that is where it stops. So, we are not going to have you do anything with demand paging and so on, but it is something you should know, because Linux will actually do this. So, when we get to the next Linux lecture, you will see how Linux is going to implement all of these, but Minix is going to do the simpler variants of this. Something like Linux, Windows, Mac OS are going to do the more complicated version of this. Okay. Any questions? Kind of run out of time. So, next time we are going to actually start talking about what Minix does as far as memory management goes.